Hi, Doc Revis here with Watch Me Work It, working electronic configuration problems. So watch me work it. In this video, we will work some electronic configurations to teach you how it's done and at the same time show you what the quantum numbers mean. So let's just get going here. Let's do the electronic configuration of nitrogen. It has 7 protons, therefore 7 electrons. So we want to do nitrogen on the periodic table. And the periodic table is arranged in S, P, D, and F configuration. So we have S, P, D, F. And we have this field order where we start with 1s, which is principal quantum number 1, 1s, and we max it out. Now S maxes out at 2. So after we have maxed out the s orbital, and we only have 1 for 1s, after we max out the s, we go to the p orbitals. P orbitals max out at 1, 2, 3, 4, 5, 6. So let's max out the p orbitals at 6, and then we have d. If we count them through, we'll see that the d has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we can max out the d's at 10. And then we have f, I'm going to squeeze in here, it's 14. Okay? So when we do this field order, which we show you here on this bottom ribbon, at the bottom here, this is a field order that we use. This field order comes from the periodic table. It's 1s2, 2s2, 2p6, 3s2, 1, 2. We skip this vacant lot, and we're over here at 3p1, 2, 3, 4, 5, 6. And then we'll go down to 4s1, 2. And then we take a little bit of a pause here when we get to the D, because the D is n minus 1. So this is going to be 3D, not 4D, but 3D because it's n minus 1. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that would be a 3D10. And then we'll pick right back up on the P side at 4. P, 1, 2, 3, 4, 5, 6. So we're going to use that order to populate nitrogen with electrons. So we're going to start with a 1s2. And so we've taken care of the max out, 1s. Now we're at principal quantum number 2, which is row 2. And that's going to be a 2s2. And now we have to finish at nitrogen, which is right here where the circle is. And so that's a 2p, 1, 2, 3. 3 slots over, 3p. So that's how we do the electronic configuration of nitrogen. And we'll check that, and we'll check it to be sure we're right. And if we count these numbers across the top, we just add them up. 2 plus 2. Let me just point to it a little better. 2 plus 2 plus 3. What does that equal? That equals 7. All right, so that's the total electrons. So we're good there. Now, one of the questions that gets asked is, how many valence electrons do we have in there? Well, the valence electrons are the total electrons in the highest n value. Our highest n value, highest principal quantum number, highest row number is 2. So we'll just add these electrons here to find out how many valence electrons. So we have 5 valence electrons. And if I want to check that, I would simply count 1, 2, 3, 4, and 5 valence electrons by counting them on the periodic table. So I have 5 valence electrons. Now, there are times when we want to draw the electronic configuration diagram. So we want to draw the diagram. So to draw the diagram, we have to add lines, bars, or circles as places to populate with electrons. So the way electrons like to populate is every 2 lines can populate 2 electrons because they like to be spin up and spin down. So we like to have one in the box spin up, plus 1/2, and one in the box spin down. Now I draw lines instead of boxes, so let me draw my lines here. So if I want to populate the 1s, an s can hold only 1. Okay, bar. because S can max out at 2 electrons. And here's how we know. Here's how we think about it. For every 2 electrons, we have 1 bar, 1 line, 1 box that we can populate. So if I have P can max out at 6, then that means I can have as many as 3, which accounts for the number of degenerate orbitals right here for P. So when L equals 1, which is a P orbital, which we'll come to in a minute, we need to make sure we put 3 bars. But for now, we're at the 2s. So we're going to put 1 bar for it. Now we're at the 2p. And for p, we have 3 degenerates because this is L equals 1. And that means we have 3 here because we have plus or minus L. And we have 3 degenerate orbitals here for L. Okay? So now I'm going to populate this. Now when I populate, okay, Pauli exclusion say I must put a spin up and spin down in the same space. Okay? But Hund's rule tells us that I must populate the degenerate levels all 1 each before I pair them. Okay? So in the case of S, well, we only have an S, so we go 1, 2. That's 2 electrons for the 2s, 1, 2. Now we're at P. Since P is degenerate and I have 3, I must populate each before I pair. So that would be the electronic configuration diagram. Now, I can also check my valence electrons. And it equals 5 again. 5 valence electrons. One of the other things that we like to know is what's the MS spin? The MS spin is whether the last electron in is spin up or spin down. Not the last electron you see, but the last electron in. So here we look at this, and so we see the last electron in is right here, and it's pointing up. Therefore, MS spin is plus 1/2 spin. Okay? Now we're going to take you one step further. All right, one more thing we want to do. Watch this. The other thing we like to know is what's the ML value, plus or minus 0. Now, plus or minus L, and including 0, which is not a plus or minus. Now, so here it is. This is like a number line with 0 in the center, and to the left is minus and plus. We can only use this having a number line form when we have degenerate levels. However, if we don't have degenerate levels, just give it a 0. Okay? Like for example, let's do the 2p because we have degenerate levels. That means to label these, I would simply put a 0 in the middle and go plus 1, minus 1. And now I've done it. Okay? All right, let's do another problem and let's not muddy it up so much with a lot of conversation. All right, here we go. Let's just play with some. Let's do, what shall we do next? Let's do germanium. Germanium's located right here. Wow, it's a lot of electrons I chose this time, isn't it? That's 32 electrons. Let's just do it anyway. So 32 electrons. So we have germanium, 32 electrons, and we have to fill it by our field order. We know we max out at S2, P6, D10, and F14. Okay, so let's just populate it. And we're going to count either on the periodic table or we're going to use the ribbon. And I'm actually doing both. So the ribbon shows you the order we're going to come in. And the periodic table does too, but you have to go 1 to 2 and back and forth on the periodic table. The way you do it, you count 1, 2, 3. Then you'll come here 1, 2, 1, 2, 3, 4, 5, 6. 1, 2, 3s, 1, 2. Then 3p, 1, 2, 3, 4, 5, 6. Then you will come here 4, 4s, 1, 2. Now we remember when we get here, pause, and remember this is 3D. 3D, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now we're right back to the 4, P, 1, 2. So let's put that down on paper. Ready? So here we're going to have 1s2, 2s2, and what comes next? Okay, 3s2. We can see it right here. We're up to here now, 3s2. Now we're over here, 3p. Okay, 3p, 3p, and we count 1, 2, 3, 4, 5, 6, or we just look and we max it out. Now we're down to 4s, and we're going to max 4s out. How do we know? Because we need to get to germanium, and it's over here in the p's. And then we have a 3d, and we maxed it out at 10, and we got germanium 1, 2. That's going to be 4p2. So that's the electronic configuration of germanium. How many valence electrons? We can count these valence electrons by looking at the highest principal quantum number. And so it's going to be 2 here equals 4 valence electrons. All right. Now, if we want to draw the electronic configuration diagram, we would have our 1s with 1 bar, 2s with 1 bar. Okay. And we skip the complete 2p right here. How did I do that? Can I squeeze it in there? Okay. All right. So 1s2, 2s2, 2p6, 3s2. Okay. All right. So don't skip anything. Good thing we caught that. So the 2p, 1, 2, 3, 2p here, and then we have 3s2 here and 3p, 1, 2, 3. It's going to be 3p, 4, S, 1, 2, 3, 4, 5 for the 3D. And then we'll have the 4P, 1, 2, 3. Okay, 4P. So let's populate it. Now in this case, we're going to populate what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Notice how I populate it. That's according to Hund's rule. One must go in each level before we pair. Then here we go. 1, 2, 3, 4, 5, 6. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, and 4p, 1, 2. Now notice that we don't feel the 4p, but we still must draw the orbital. That's because they're degenerate. You must draw all the degenerate orbitals. You can't leave them out just because you don't have electrons in them. Therefore, a good practice is to draw out the orbitals first before you start to populate. That way you won't forget to do that. All right, so let's check the valence electrons this way. The valence electron is going to be 2 here and 2 here, and that equals 4 valence electrons. We can check the spin on this. The spin, the last one in, was plus 1/2 because it's spin up. Okay, we could check the location, that is the plus or minus L, by putting a 0 in the middle, and we have a plus 1 here and a minus 1 here. Our last electron in is in the 0. Our first electron in is in the minus 1. Okay. All right. Let's do another one. Let's do another one here. What shall we do? Let's do, let's just do iron. Right, located right here. So iron has 26. So we know how to go right to work here with the ribbon. And this time I'm not going to skip anything. 1s2, 2s2, 2p6. I know I have to work until I get to a 3D 1, 2, 3, 4, 5, 6. Okay, so let me keep working until I get to 3D6. So 2s2, 6, 2s2p6. 1, 2, 3, 4, 5, 6. Now I'm down to here. There we go. Pick up. And we go here. And then we'll go 3p6, 4s2. Pause and put the 3d. 1, 2, 3, 4, 5, 6. 3d6. Okay. All right. So we have that. And we want to draw electronic configuration diagram. We have to draw all the orbitals. We can't leave any out, whether they're filled or not. We have to put them in there. Okay, 3s, 3s, 3p, 3p, and 4s. And then we have the 1, 2, 3, 4, 5, which is the 3d. And so now we'll just populate 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1. I use half arrows. They're just convenient for me. And here, and then we have to go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And there we have it. And the last spin in is ms minus 1/2 is the last spin in. And then we have all these unpaired electrons. So that's how we do the electronic configuration, fill them in. Oh, let's just do this location for you too on this D. The way you do the location, find a center point. That's a 0 on the number line. Then you go plus 1/2, plus 2, or you go minus 1, minus 2, not 1/2. You go 0, plus 1, plus 2, and then minus 1, minus 2. Okay, so that's how you do the electronic configuration and a few other things related.